Okay. So, who shot a rocket? Yeah? Oh,
well, more, actually.
Only one person.
Many more.
Whose rocket was successful? And whose rockets misfired? And, and was it fun? Yeah? Oh, okay. All right. So, Jörg is going to do us the honors of telling us who the winner was.
Actually, we had quite some fun out there. And, well, we have a winner, but I was very amused about the second place. There is one person among us who knows best about flying rockets, and that's Mr. Nicollier. He made an astounding 4.03 meters. But we had somebody whose rocket flew even better to 5.02 meters. And that's Marc Mouchet. Come up, come in front.
Come up. We have a prize for you. Yeah.
Thank you.
Well done.
So thanks for participating. I think it was fun for those who like to see real rockets, bigger rockets, louder rockets. As I said before, come join us. We will be glad to tell more. Have fun.
Thank you, Jörg. Jörg actually put in a lot of effort helping us to prepare this, so thank you. Okay, so let's get going with the next speakers. Valentina will introduce Giulia, our next speaker.
Yep. So the next speaker, it's a surprise for me because she comes from my same hometown, and we just discovered that we are now both in Zurich. And so Giulia came out like a space engineer at RUAG, and she decided to study space engineer after she watched too many times Apollo 11. That is also one of my favorite movies. Was 13, sorry, but 11 was the one successful. So it's a pleasure to introduce you. So Giulia Paoli will talk about to infinity and beyond, how do we reach space?
Sorry, I can do this. It's all right. Because yes. It's all right. I'm the only one with the first. Yeah. It's all right. And speak. Okay, perfect. Thank you.
So, thanks everyone. As Valentino introduced me, I am a space engineer. I studied aerospace engineering. And tonight I will talk to you about how do we reach space. So space has always been in a man's mind. This is a poem from a poet who lived in Greece around 400 years before Christ. And what he was wishing to his lover was to give him wings to fly around the world. And we always looked at the sky either to write poems or to understand what's out there. And some of us, maybe like me or like you, just enjoy the view of a nice star sky. But some other people actually contributed a bit more to what is today rocket science. So I put together my personal Fab 5. I consider Galilei and Newton as just one. So these basically are my favorite persons who contributed to rocket scientists. The first one was, again, a Greek guy. And his name was Archytas, and he lived again around 400 years before Christ in Greece. And what he did, so he was a philosopher, a mathematician, and an astronomer. And what he wanted to do was to build something that could fly. And to do that, he decided to build up a bird. Bird is flying, so he wanted to create something that could reproduce something that in nature is flying. And to do so, he created this small device, which was the shape of a bird, and that was moving thanks to a stream of compressed air. Now, obviously, Archytas wasn't aware of the fact that he actually built the first rocket we are aware of in our history. So that's why I put him as the first place. After him, of course, we have Galilei and Newton. They are known because they were incredible scientists and geniuses. But why are they important for rocket science? They're important because they were the first who put in equations the law of motions. Galilei contributed with the idea of inertia, and then Newton with the law of motion. And these are really the basic of rocket science, and we will see afterwards why. And if we then jump up to the 20th century, we jump to Russia, and this guy there is called Konstantin Tsiolkovsky. He was a space pioneer, actually. Even though he never flew to space, he was the first one who imagined about colonizing other planets. He was imagining about producing energy with solar panels, and he wrote one of the most important equations for rocket scientists, which is the Tsiolkovsky equation, which links the variation in velocity of a rocket to the variation of its mass. More or less at the same time, but this time in the US, Robert Goddard was also studying extensively rockets, and he managed to fly the first liquid fuel rocket. And that opened the door to the last guy, who is my personal hero. He is Wernher von Braun, was a German guy who flew to America after the Second World War, and was the father of the Saturn V, which is the biggest rocket ever built, and was the one that brought the man to the moon. And here you see, so these things here is one of the, I think, 5 nozzles which compose the first stage of the Saturn V. But, so now I introduced you velocity, mass, equations. So, but what is exactly a rocket? When we talk about rockets, technically we are referring to a type of engine. And in particular, a type of engine that inside itself has the propellant and the fuel. So unlike what we use for aircrafts, for instance, where we have the engine, which has the fuel in the airplane, but then takes the oxidizer from outside, takes the air, in a rocket you have already everything. So that's the very specific feature of the rocket engine. And as I said before, to really understand how a rocket works, we have to step back and go back to Newton. So he wrote these very, very basic 3 laws which describe motion. Now, the first one states that an object at rest remains at rest, whereas an object in motion remains in motion on a straight line, unless acted upon by an unbalanced force. The second one says force equals mass times acceleration. And the third one says that for every action exists an equal and opposite reaction. Now, I can see your faces. You're thinking physics, boring. No. And I will explain you why. Actually, think about a very simple example. We can see these 3 laws in our everyday life. Think about a kid holding a ball. He's at the park. He wants to play with his friends. He's holding his ball in his hands. And actually, while doing so, he is having an object at rest, which is the ball, on which a set of balance forces is acting, because he has the gravity force pulling the ball towards the Earth, and the kid itself, through his muscles, is exerting an equal and opposite reaction to hold the ball at rest. Now, let's say that the kid was to shoot the ball and to kick it, and then he kicks it with his foot. And then, with his foot, he's exerting, he's unbalancing the condition of the ball itself. When the ball is not anymore in contact with the kid's foot, then it's again flying. And what happens to the ball? If we are on Earth, what happens is that eventually the ball will fall again down to the Earth. Why? Because we have drag due to the air, and we have always the gravity force. But if you for 1 second imagine to be not on Earth, but in deep space. So you are away from any gravitational field, you don't have air drag because you don't have air in space, and then you kick the ball. As soon as the ball is not anymore in contact with your foot, then your ball is an object in motion, which will remain in motion on a straight line. Now, how do we apply these 3 simple laws that I try to explain with a everyday life example, 2 rockets. So here you see a very, very simplified scheme of a rocket. But actually, what I said just 1 second ago about the ball, we can say again about the rocket. Imagine a rocket standing on the pad before launch. Then what's happening? It's an object, it's at rest, nothing is acting on it. You have the gravity, which is trying to pull it down to Earth, but then there is the pad, which is exerting an equal and opposite reaction to it. And now we want to move it. And to do that, we have to create a force. And we have to create a force that is bigger than the gravity. Doing so, we can allow our rocket to lift off. To do that, what we do is to mix up, in this case, we have hydrogen and oxygen. We mix them up and we burn them. While these two burn together, what happens is that they create a very hot gas, which is then accelerated through the throat and the nozzle of the rocket. These gases, with a high acceleration, and then creating a force acting towards the Earth, which creates then a reaction, opposite and equal, which allows your rocket to lift off. Now, if any of you ever saw a rocket lifting off from the pad, you must probably notice that it's quite slow. You would expect that it's jumping like the small rockets we saw before, but actually it's quite slow. And that's due to the concept of inertia, because it's true that we have the gases which have high acceleration, but also a low mass, which creates a force, and then an opposite and equal reaction, which lift off the rocket, but the rocket has a bigger mass, so its acceleration is lower, due to the second law, of Newton. Now, to let you understand a bit better, I would invite you to look at this video and pay attention to it. So this is the Saturn V rocket. I hear someone laughing, so someone saw the detail I was talking about. So this is a funny video. It's not really accurate, technically speaking, but it's just to give you an idea of how much fuel we would need to lift a rocket. So the Saturn V, as I said, is the biggest rocket we ever built, and he's approximately, I guess, around 20 meters taller than the Statue of Liberty. And just the first stage is actually burning approximately 2,000 tons of fuel. Now, if you consider an elephant, how much is it? 4, 6 tons. It means that for the 2.5 minutes during which the rocket is, the first stage is burning, you basically have per second between 3 and 4 elephants shot out of the nozzle. So you can just imagine one, boom, 3 elephants just went out. And that's what you need to lift off your rocket and to create a force that is able to bring you out in space. Now, let's say that we are out there. Let's say that our rocket was accelerating, and you have basically 2 possibilities. Either you're accelerating so much and your force is so big that you reach what we call the escape velocity. On Earth, it's approximately 11 kilometers per second. And this velocity is the velocity you need to escape the gravity of Earth. And then, in that case, you would just stay on, basically, you would be again in a balanced force situation, and you would stay in motion on a straight line. Or, most of the time, you don't really want to travel towards the deep space, although there are some spacecrafts who are on their way there, for instance, the Voyager 1. But most of the time, what we want to do, as we heard before, we want to use space to have some benefits for us. And which benefits can we have? For instance, communications, or we can monitor the Earth. And to do that, most of the time, we need to be on an orbit around the Earth. And the orbit are exactly what you need to move in space. Because imagine, I'm a satellite, I reach space, and what do I do then? When I'm on Earth, I can take a tram or go to the motorway, and then I have indications. I want to go to Lucerne, I want to go to Basel, I know where I have to go. But in space, you have nothing like that. What is working like a motorway in space are the orbits. And to understand a bit better how an orbit works, Now here I just put an example of the orbits that we can have around the Earth. But the principle of an orbit, it's really simple. So everything is based on velocity and energy. So you have to imagine, as I said before, if we are away from any gravitational field and we have a certain velocity, we would tend to move on a straight line with that velocity. On the other hand, if we are close to the Earth, then what happens? Let's imagine that this table is the Earth and I'm a satellite. I have a certain velocity, I would tend to go straight, but on the other hand, I have the Earth there, which is trying to pull me with its gravitational force. So what happens to my trajectory is that it won't be straight, but it would start to get curved. And that's exactly how the orbits are then formed. And so that's what you need to move out there. And you can have different type of orbits with different types of velocity for different type of purposes. So for instance, if you want to monitor a specific area of the Earth, you would need a geostationary orbit, which is an orbit which is basically moving with the same velocity as the Earth, so it can always control and monitor the same area on the ground. If, for instance, the International Space Station is orbiting at a LEO, which is a low Earth orbit, it's approximately around 400 kilometers above our heads. So that's what you actually need when you want to move out there. So hopefully now you understood a bit better how do we reach space and how do we move there. But which are the new challenges? I mean, you see here, I guess all of you recognize the Starman, which has been launched with the SpaceX Falcon Heavy, and is supposed to reach Mars. Let's see if he will really reach it or not. But there are so many other challenges, apart from the spectacular view that we have from this picture. There are so many other interesting challenges that we have. We have both in the development of rockets to try to make things more efficient, to try to optimize the mass, to make things less expensive. But we also have many other challenges when we want to explore space. And for instance, not only for observation, but also to understand more about our galaxy and what else is there. So, thank you for your attention.
Questions, or do we have time? Is there, if you want, you can go and maybe later, okay. So the next speaker is again an astrophysicist, sorry, but since I'm there, I knew a lot of them. So it's my pleasure to introduce you a postdoc of the University of Zurich in the Institute for Physics. And she's Maria Haney. She's a postdoc researcher at university, and she's really special because she worked on LIGO, and she's an expert of black holes and gravitational waves. So, thank you so much.
Yes, so I am originally a theoretical astrophysicist, but since the last 3+ years, since the first gravitational wave detections, I can also call myself an astronomer. So my talk is not really connected at all to Yuri Gagarin, but I actually have a story about Yuri Gagarin, because when my mother was a child, she actually met Yuri Gagarin when he was on his victory tour through the Eastern Bloc. And to greet him, they were instructed, she and her friends, to take a bucket and wrap it in tinfoil and cut out 2 eye holes and put it on as a space helmet. And this is how my mother met Yuri Gagarin many, many years ago. Okay, so I want to give you a brief walk through the gravitational wave observations and through their impact on our understanding of the universe. So unfortunately or fortunately, we cannot talk about gravitational waves without also talking to some extent about Einstein's theory of general relativity, which was published a little more than 100 years ago. And unlike Newtonian gravity, in relativity, gravity is actually not a force. Gravity is an effect of space-time curvature. And you have to imagine that if you have a mass in the universe, it will curve space-time locally, and then any free-falling smaller object will move on a path that is dictated by the space-time curvature. So in analogy to electrodynamics, the theory of relativity also allows for wave solutions to a particular linearized weak field prescription. And these gravitational waves are what we call ripples in the fabric of the universe. So you will have an accelerating mass, an accelerating massive object, which will distort space-time locally, and then this space-time curvature will travel outwards from the source at the speed of light. And you can see this on this animation, which I hope will work. No. Oh. So you can actually see the squeezing and the stretching due to the passing gravitational waves. And as you will see that depending on where you are in the space-time, the light travel time between 2 points will increase or decrease. So any accelerating objects emits gravitational wave. Even a U, for example, if you are asymmetric and you spin around in a circle, you will emit gravitational waves, but these will be very, very small. So astrophysical sources of gravitational waves are usually cataclysmic events in the universe, like merging neutron stars and merging black holes, which are the events that we've so far seen with LIGO. So what are these sources and how are they formed? So when a star dies at the end of its life, so when all its nuclear fuel is spent, it will collapse under its own gravity, usually associated with a supernova. And if this star is massive enough, the object which will be left behind is a very small, very dense star out of closely packed neutrons. And these neutron stars are actually the smallest, densest stars imaginable. They usually have a mass of 1 to 2 masses of the suns with a radius of only 10 kilometers. And for comparison, our sun has a radius of 700,000 kilometers. So these are very dense objects. And on the pictures here, you can see observations of the Crab Nebula. In the red one is the optical observation, and the blue one is the X-ray observation. And you can see, if you look closely, the neutron star is the central object, and then around it the ejecta of the supernova. So if this star, the progenitor star, is very, very massive, the neutrons or the pressure of the neutrons themselves will not be able to hold the further gravitational collapse, and the object will collapse even further into an infinitely small, infinitely dense object, which is a black hole. So in a black hole, all the mass is essentially in a single point, and this singularity is hidden behind the so-called event horizon. So the singularity can have a mass of tens of solar masses, or it can have masses of millions or billions of solar masses. In these supermassive black holes are objects that we expect to find at the centers of galaxies. And the event horizon is essentially what shields the singularity from our view, because the event horizon is the point of no return for any light, any matter, or even an astronaut which is falling into the black hole. And the region beyond the event horizon is not accessible by us and is essentially cut off from the rest of our universe. So what will happen to an astronaut if he or she has the misfortune to fall into a black hole? When they pass the event horizon, nothing will happen because the event horizon is a purely property, and so they will not experience anything. But as they fall towards the singularity, they will start to experience the tidal forces of the black hole. So essentially, they will experience a gravitational gradient at different parts of their body. So they will be stretched from head to toe, and they will be horizontally compressed. And as they fall further towards the black hole, eventually they will be ripped apart. And there are other scenarios. There are other scenarios because, as you may know, general relativity is not or is violating the concept of quantum mechanics, so basic concepts of quantum mechanics, especially the concept that information cannot be lost, because any information which falls behind the event horizon is lost. So there is another scenario which is violating GR, but which essentially says instead of the event horizon, you have a boundary, which is a wall of pure radiation, a so-called firewall. And when the astronaut is essentially incinerated on impact. So fortunately, we are very, very far away from such black hole sources in the universe. So the only way we can see these strong field effects of gravity is by looking at gravitational wave data, which we finally have now. So maybe very briefly something about the history of detecting gravitational waves. The first indirect evidence of gravitational waves came from the observation of the first binary pulsar, the so-called Hals-Taylor pulsar. So this binary pulsar is a bound system of two neutron stars, one of which is rotating. And because of the rotation, the neutron star is sending a light beam, which we observe on Earth as pulses. So general relativity predicts that while this bound system in spirals, orbital energy will be lost through the emission of gravitational waves. So general relativity predicts a certain amount of orbital shrinkage. And by observing this Hals-Taylor pulsar over years and decades, we have found that the orbital shrinkage agrees with the predicted orbital shrinkage incredibly well. But since the very early days in the 1960s, there were efforts which were pioneered by Joseph Weber, which was an American scientist, to detect gravitational waves directly. And the way he wanted to do that is he wanted to use resonant bar detectors, which are huge aluminum cylinders, and through a squeezing and stretching of these resonant bars. And he actually claimed in the 1960s that he had detected gravitational waves. And there was a lot of excitement, but this was never independently verified. So he believed till the end of his life that he had detected gravitational waves for the first time, but no one took him seriously, and he became very bitter. So the modern concept of gravitational wave astronomy is laser interferometry, which was independently invented, well, it was not invented, but as a concept by Soviet scientists, but I think more well known now, Rainer Weiss in the 1960s, and he was one of the 3 people who received the Nobel Prize last year. And the basic concept of laser interferometry is that you are going to look for relative changes in the arm length of a Michael-Morley interferometer, which I will explain in the next slide, due to a passing gravitational wave. And nowadays we have a network of such detectors on Earth. This is the one of the 2 LIGO detectors. I think this is the one in Louisiana and Livingston, I'm not quite sure. We have the Virgo detector, which is a European detector in Italy. We have GEO-600, which is a small detector in Germany, which was supposed to be a larger detector, but then because of German reunion, no money was there, and now it's only a small detector, which is basically doing research and development for the big detectors. There's Kagra, which is an underground detector in Japan, which will come online very shortly. And there's also the proposed 3rd LIGO detector in India, which will maybe start taking data in the 1920s. So how does laser interferometry work? This is the basic concept of LIGO. So essentially, you are sending laser light through a beam splitter, and then the beam is split along 2 perpendicular paths along the 2 arms. The arm length of LIGO is 4 kilometers, and at the end of the arm, light is reflected back by a suspended test mass. And actually, what you have here is you have a resonant cavity, an optical cavity. So the light will be bounced back and forth a couple of times in this optical cavity. So essentially, your effective arm length is much, much longer. It's of the order of a couple of thousand kilometers. And then eventually, the light will be recombined and then will be read out by a photodetector. And what you're looking for is for a change in the interference pattern of the light due to a passing gravitational wave, which is expected to stretch this arm in this direction while squeezing this arm in this direction, thus changing the interference pattern. And we have 2 LIGO detectors at opposite ends of the US. This has a very good reason, because to eliminate any local disturbances, we are looking for coincident detections in both detectors. So within a certain time interval that it would take the gravitational wave to travel from one detector to the other, any detection has to be happening in both detectors. And if you look at this plot here, this is the sensitive frequency band of LIGO from around 20 hertz to a couple thousand hertz. This is a very noisy detector because Earth is a very noisy place. And if you look, for example, at the lower bound of the frequency range, 20 hertz, this is about as low as we can go on Earth above ground, because there is just certain seismic noise here which we cannot eliminate, even with best isolations. But this is still one of the most sensitive instruments which has ever been built by man, if not the most sensitive, because actually the relative arm length that we're detecting is of the order of 1/1000th of the diameter of a proton. And to put that into perspective, the measurement is essentially similar to what it would be to measure the distance to the nearest star outside of our galaxy to the accuracy of a width of a hair. So what are we actually detecting? What have we detected with this first direct detection of gravitational waves in 2015? So on this upper plot here, this is the clean data. This is what the detector is seeing. So this is essentially a measurement of the relative difference in arm length over time in both detectors. And then on this second panel, you have the pure gravitational wave signal that we have extracted from the noisy data. And then if we subtract the signal from the data, we actually are left with pure noise, which tells us that we have truly detected a gravitational wave. And then this colorful plot on the bottom is the time and frequency spectrogram in both detectors. So essentially, this is the power which is radiated at each time and frequency. And here you can clearly see the characteristic chirp, upward chirp in frequency over time, which we expect from such a binary system of compact sources made out of black holes and neutron stars. And in particular, what we're observing, or the physical scenario we're observing, we have two black holes of the order of a couple of solar masses, which are inspiraling. And we only see a very short part of the inspiral because everything before is outside of the sensitive band of the detector. And eventually, these two black holes will become so close that they touch and will merge into a single object. This is happening here. And then afterwards, this object that we're left with will ring down, what we call ring downs, will oscillate for a couple of times until it settles down into its final state, which is a spinning black hole, which is no longer radiating gravitational waves because it no longer has any asymmetries. So if you look at the table in the bottom, with some very complicated data analysis, we can extract from the data to some accuracy the parameters of the source that we're looking at. And if you look at this closely, so the combined mass of the two components before the merger is of the order of 65 solar masses, while the mass of the final black hole that we're left with is 62 solar masses. So where did these three solar masses that we're missing, where did they go? They were radiated away in gravitational radiation. And to put this into perspective, this is this energy which has been radiated away in gravitational waves is larger than the power which is emitted in light by all the stars in the known universe. So this is an incredibly highly energetic event that we're seeing. And now I want to show you a quick video. This is not an actual observation, this is a simulation of this source. And this simulation is only possible by simulating the motion of the source in the gravitational radiation with some very, very complicated numerical simulation that is attempting to solve the highly dimensional problem of full general relativity numerically, and this takes a lot of computing power. So we can't do that for all the data analysis, but we can do it for illustrative purposes here. So this is what you're seeing essentially now is something that happened 1.4 billion light years away. And that is so long ago, that was at a time when there was not even multicellular life on Earth. So we're looking far back into the past. So this simulation is slowed down significantly because the signal that we're observing is actually only a fraction of a second long. Okay, you can see the two black holes in spiraling as we're zooming in. This three-dimensional effect is a measure of the space-time curvature, and the colors from green to red are basically showing you the time dilation. You can see that the time slows down to infinity as you're going closer to the event horizon. And then, as you will see later, the blue to purple colors are the gravitational waves which are propagating outward from the source towards us. So we're getting closer, we're approaching the merger. And now time is frozen, so we can look at the merger more closely. And now the event horizons of the two objects touch and form a single object. And that is stretching and squeezing a little bit around its final state until it settles down and no longer emits. We can actually also listen to gravitational waves because gravitational waves are in the frequency band that is audible by the human ear. So we can hear the sound of gravitational waves after some data processing. So what you will hear now is essentially you will hear the chirp signal first twice at the original gravitational wave frequency, but this will be a very faint sound. And then for educational purposes, this has been frequency shifted to a higher frequency, so you will hear the same signal twice again, but at a higher frequency, but still at the same length. And this will be a much more audible sound, and then this whole sequence will repeat once more. And what you should hear is you should hear a chirp like whoop upwards, ideally, if this video works. We don't do anything. It's not working. Oh, audio is not working. So this is what you should have heard. If the audio were working, this whoop sound is what you should have heard. But you can also find this on the internet, I'm confident. So, as you know, we just did not have this one detection of binary black holes. We had a couple. We had 4 unambiguous detections so far, and then a couple of marginal events. The one that you see at the very end is the first detection that was made, not just by the LIGO detectors, but also by Virgo in August. And what we know from these observations is that what we had assumed previously about the maximum mass that these stellar mass black holes can have was underestimated. We had estimated from X-ray studies that they would have maybe tens of solar masses, but what we found actually is we found black holes, stellar mass black holes of the order of 60, 70 solar masses. These events that we observed give us an understanding about the rates with which these events are expected in the universe. And what we can learn from looking at the gravitational wave data itself is we can know something about the source parameters, and the source parameters tell us something about the process and the environment in which such black holes are formed. In particular, for example, if you're looking at the magnitude and the direction of the spins of these component black holes, that would gives you a pretty clear indication about whether these binary black holes are formed in isolation or whether they are formed in very dense stellar environments like active galactic nuclei or globular clusters. But so far our observations do not have really reliable information about the spin, so we cannot really make this distinction, but we hope in the future and with more observations we will be able to say something much more clear about the formation process of binary black holes. And then one other thing that we're doing is that black holes, because they are pure gravity and they have no effects of matter, are very good systems, clean systems to test the postulates and the hypothesis of general relativity. So we are subjecting our data to a whole barrage of tests of general relativity, and we're basically looking if all the postulates that we know hold up with the GW data. And for example, one thing that we're doing is we're looking for the effects of dipole gravitational radiation in the signal, which we know is forbidden in general relativity. We look for violations of the equivalence principle and all kinds of other tests. So these are very good systems for that as well. But we haven't just observed binary black holes. In August as well, we have seen an entirely new source. And also for the first time, this is a source which was not just seen by gravitational waves, it was also observed in the electromagnetic spectrum through a huge multi-messenger effort. So what the LIGO and Virgo detectors essentially saw was the in-spiral signal from merging binary neutron stars, which is this very faint track that you can see here in the both LIGO detectors. And the fact that it was seen in all three detectors, well, actually was not really seen by Virgo, but the fact that Virgo did not see it, that it was in Virgo's blind spot, actually told us something about the localization of the source and allowed us to localize the source fairly precisely as opposed to other gravitational wave detection. For example, here you can see the localization with LIGO, only LIGO, and here with LIGO and Virgo it's much smaller. And then about 1.7 seconds after we detected the signal, the Fermi satellite detected a gamma ray burst from the same location in the sky. And the gamma ray burst is a sudden and massive emission of gamma rays, which is the brightest electromagnetic event in the universe. And Fermi detected such a gamma ray burst, which seemed to be associated with our gravitational wave source about 1.7 seconds after. And then about the next half hour, a coordinated effort to look for other optical transients was started. And a couple of optical telescopes actually managed to see an optical transient from the same direction and managed to identify the host galaxy of this source. And this was the first time where we could pretty much unambiguously identify where does our gravitational wave signal come from. And then in the next 2 weeks, all other transients were also found, the electromagnetic spectrum, X-ray transients, radio transients, all apparently coming from the same source. And if you look at this table, this is not very visible. You can see that what we extract from the gravitational wave data about the parameters of the source, we have masses of the two components of about 1 to 2 solar masses, and this is an indication that this is indeed a binary neutron star event. And here, it was compared to the binary black hole, only about 5% of the energy which is lost is radiated away in gravitational waves, and the rest is radiated away in electromagnetic radiation. So just very briefly, because I need to come to the end, some things that we learned from this event in particular is something that we only suspected so far, namely that gamma ray bursts and other bright electromagnetic events like kilonova are indeed produced by neutron star mergers. And then especially from the fact that we observed a kilonova, which is a very specific strong type of electromagnetic radiation, which is due to the the decay of radioactive nuclei, heavy nuclei. We can infer that neutron star mergers are chemical factories for gold and other very heavy elements, which is something we did not know before, because so far we knew that light elements like helium and hydrogen are formed by the Big Bang, and then heavy elements are formed in this collapses of massive stars. And then also from our data, we can infer something about the state of dense matter under extreme conditions, in particular about the neutron star equation of state. And since we have now a distance measurement, not only from gravitational waves, but also from the electromagnetic observations, we can confirm one of the basic postulates of general relativity, namely that the speed of gravity is the same as the speed of light. And we can even use gravitational waves as standard sirens to measure the age of the universe. So on my final slide, a brief outlook to the future. Where do we go from here? Later this year, LIGO and Virgo will start their third observing run. Maybe Kagra, the Japanese detector, will also join for the first time. And the detectors have been upgraded recently, so we expect a much improved sensitivity, and we expect many more sources. And then further in the future, there's a new generation of gravitational wave detectors which is being proposed. One of them is the Einstein telescope, which is only proposed so far, not funded. And this is going to be an underground detector with an arm length of 10 kilometers. And because we are eliminating a lot of noise in such a scenario, we expect to be able to go to lower frequencies and observe these LIGO-Virgo sources at an earlier stage. And then also, and after this has been a long odyssey through the funding agencies in the EU and in the US, the laser interferometer space antenna has finally been accepted as a large-scale ESA mission last year, and it will be launched in the year 2034. And this is a space-based gravitational wave detector with an arm length of 2.5 million kilometers, which will trail behind Earth and follow it around the sun. And this will be a much, much, much lower frequency range where we can expect to observe sources which we simply would never observe at LIGO, like supermassive black holes in the center of galaxies or extreme mass ratio inspirers. Thank you.
Thank you. Wow, heavy, heavy stuff. Mentally and literally, and especially for this time of night. Oh, she's gone already. Thank you so much. Okay, so seeing as time is really getting on, we are really, really pleased to be, to be presenting our, welcoming to the stage our highlight speaker, Claude Nicollier, national hero. I mean, because I'm not from Switzerland originally, I had to learn about Nicollier, and I was absolutely delighted when I realized that this is the gentleman, the astronaut who repaired the Hubble telescope. So really, he's like the ultimate cosmic handyman. And thanks to him, humanity has now been able to see deeper and further into the universe than ever before. And this, thanks to this man. So, what we'd like to do now is we'd like to invite Ben. Where are you, Ben? You're hiding in the back here.
I know it's famous, but let's introduce better Ben. So Ben Moore is a professor at the Institute for Computational Science. And he's very famous here at KOSMOS, like a resident
he's so famous.
astronomer.
You know, you can buy him for 5,000 francs for a one-night stand, but it includes a telescope. So we'd like to invite Ben to the stage because we feel that he has a personal connection with Claude that we'd like him to share with the audience. Yes, please, we'll set it up.
Thank you. Good evening, ladies and gentlemen. Indeed, I was auctioned off at a charity event just last month, and someone actually paid $5,000 to spend the night with me observing the stars. So looking forward to that. It's going to be wonderful. Now, we're coming to the close of the evening, of course, and I don't think Claude needs too much introduction, although just a few words, because Claude is a very humble guy. I'm scared of flying. I mean, just going up into an aeroplane, you know, I'm shaking, and Claude, he's been into space 4 times. He spent 1,000 hours up there orbiting the Earth, and I'm going to have a little chat with, after Claude has spoken, I'm going to show a few slides for us to stimulate the discussion with Claude about none other than, of course, going to Mars and Elon Musk. Of course, we have to do that. And but Claude is a very humble guy, and as I mentioned, I would tattoo on my forehead, you know, I've been to space 4 times. And what's special about Claude, not only has he had this accomplished career, he's trained as an astrophysicist, he's a professor and lecturer at EPFL, Lausanne, but most of all, he just loves educating people. He loves teaching people about science, about space. And I had the pleasure of working with Claude when my wife and we wrote our last book, Are There Aliens on the Dark Side of the Moon? And Claude wrote a most beautiful foreword for this book, and we hosted a sellout event at the Kaufleuten where Claude happily answered the questions of dozens of children for hours on end, and he just stimulated them so much. I think we've got a generation of new astronauts coming online. So I will pass over to Claude, and thank you very much for being with us tonight.
Well, thank you very much, Ben, for these kind words. We have had a full program tonight with Valentina on Gagarin, that was very good. Kamlesh on the space law. Joachim on the overall structure of the universe. Giulia, a wonderful lesson in classical physics and the rocket equation. And then Maria, this is unbelievable. And you have to remember there is a test at the end of this session today. And the ones who pass the test will be invited to YURI'S night 2019, but the other ones will not be able to go. I thought it was a very, very stimulating evening. And what I'm going to talk about tonight is very simple, because this is a talk of an astronaut, so it has to be really basic and simple. So you can relax, no equations, no general relativity, no complex statements. It's going to be very basic, because I'm just an astronaut. Basic. Let me see if this works here. Can I have the sensor for this? So it's not installed here. Yeah, okay. Just a little detail here. Okay, anyway, again, something very, very simple and basic, and I thought I'd talk to you about space travel, a user's guide. And I use as a title picture a picture that is, for me, very, very touching. This is Bruce McCandless, an American astronaut, on a spacewalk in 1984. This was 3 years after the beginning of the shuttle program started in 1981. And he went on a spacewalk, and he had a small personal spaceship in the payload bay of the shuttle. And he took it and went away from the shuttle about 200-300 meters, untethered, without a safety tether, ohne Sicherheitskabel. And he flew formation with the shuttle at 28,000 kilometers an hour on his little spaceship. On the right hand, he had a rotational hand controller. He could control the pitch, the roll, and the yaw. On the left hand, he had a translation hand controller. This is one axis, this is another one, and this is three degrees of freedom. This is unbelievable. This is the ultimate adventure of human spaceflight. Bruce McCandless. Okay, again, I'm going to be very basic, but I'll tell you a few things about astronauts, becoming an astronaut, the training, the thing you have to go through. But first of all, I want to honor Gagarin, because Yuri Gagarin opened the door of space for us, and we have a lot of respect for him. Kamlesh talked already quite a lot about, well, we had a very first presentation on Yuri Gagarin, but it was mentioned already the kind of orbit that he had and the achievement that he went through. At the time, we were not absolutely sure that a human being can survive the space environment. And of course, Valentina had a very complete biography of Yuri Gagarin. This was shown already, I think, by Kamlesh, the orbits of this single orbit in about 108 minutes with the lift-off from Baikonur. This is a spaceship that has been shown already, and touchdown 105 minutes later. I would like to say that we need to honor other astronauts this day, the 12th of April, because exactly 20 years after the remarkable flight of Yuri Gagarin, we had the first shuttle flight. And we had two very brave and talented American astronauts, John Young, commander, Bob Crippen, the co-pilots, who flew the first shuttle mission exactly 20 years after the flight of Gagarin. And I think although this day is devoted to Yuri Gagarin, we need to mention these also, because they are very courageous and remarkable astronauts. John Young passed away just a few months ago. He was a very close friend. I have a lot of respect and admiration for him. He was a commander of Apollo 16. He flew 2 times on Gemini before, commander Apollo 16. And I remember he was telling me, Claude, STS-1 was more dangerous than Apollo 16. And it was. Because Apollo 16 was Apollo 16. We have had 11, 12, 13 didn't go too well, but the crew was saved. 14, 15, then 16, the system was running pretty good, but the space shuttle, this completely asymmetric vehicle, not tested previously without the crew, went off from Kennedy Space Center, Florida, with John Young and Bob Crippen. I was there with my family, I remember, with many astronauts from Houston, and it was really like this, remarkable. And again, I think we should celebrate also this first flight of the shuttle with John Young and Bob Crippen and honor these 2 astronauts. That's a liftoff of Columbia, which unfortunately was destroyed, as you know, in 2003 in the second shuttle accident of history. But this is a liftoff of STS-1. And again, we were so scared. It went fine. It was a very successful 2-day mission, but it was a very dangerous mission. And this is a picture that was not sent during the mission, but it was brought back by John and Cripp. You see that some of the thermal protection tiles were missing here. And the enormous fear that we had was that some thermal protection tiles maybe were missing also on the bottom of the orbiter, which is a very large surface that was getting the highest temperature during the re-entry. So there was a lot of scare. Is that going to be okay for the re-entry or not? Because they were reporting verbally that there were missing tiles in the back of the fuselage of the orbiter. Everything went fine. I remember there was a blackout during the re-entry because of the plasma sheath around the space shuttle during the hot part of the re-entry was such that electromagnetic waves were not going through, so there was a blackout. There was not much later in the shuttle program because we're doing communication via tracking a data relay satellite, which was in the wake of that plasma sheath. So via this relay satellite, the electromagnetic waves or radio waves were getting to the orbiter in both directions. But on that first flight, I remember we had blackouts. And you know, the re-entry of a winged spaceship at 26 times the speed of sound coming in the atmosphere had never been tested before, and we were really like this. And suddenly we heard the cracking of the radio, and then we heard John Young saying, everything is fine. What a relief. And again, beyond Gagarin, I would like to honor John Young and Bob Crippen. Bob Crippen is still alive. John Young lost his life a few months ago. This is a landing at Edwards Air Force Base on the large lake bed. And this is John Young, who came down the stairs. And this is Bob Crippen coming down the stairs, but holding the handhold, because after even a few days in zero gravity, you need to hold yourself when you come down. This is remarkable. And look at this. This is a cockpit, like the cockpit of an airline. You see all these tiles that had gone at 26 times the speed of sound through the atmosphere. Again, that was a remarkable achievement. Anyway, you understand my idea here. Yuri Gagarin, John Young, and Bob Crippen are honored tonight. Okay, are you interested in going to space? Raise your hand, the one who might be interested. Okay, so that's about 1.5 hours, I would say. There are two options. Either you can go as a tourist, and these are two tourists who went into space. Tito paid about $20 million to go with the Soviets. No, it was with the Russians. It was, I don't remember the year exactly, 2007 or 2008. 10 days in space with the Soyuz onto the International Space Station, spent some time there. And this is Guy Laliberté, a Canadian who also paid about the same amount, $30 million, to be the second space tourist in the history. You can choose to do that. It's pretty expensive, but you don't have to go through the astronaut selection process and training process. There's a little bit of training, but not that much. Or you can be a pro. And these are two real pro. This is Neil Armstrong. God knows that he's a pro. And this is Scott Kelly. I flew with him on my last mission in 1999 on the third servicing mission of Hubble. He was a co-pilot. And he was twice on the International Space Station, 2 times for, well, the first time for 6 months, the second time for 1 year, 1 full year. He's one of the few astronauts who spent 1 full year at a time in the International Space Station. These are real pros. These are tourists. With all the respect we have for them, but that's different. Now, this is a little complicated, but I want to explain that carefully. Space tourists, it costs you about $200,000 to go suborbital. This is what Virgin Galactic is going to be offering pretty soon. Go up and down. I'll show a video in a few minutes about the suborbital flight. You don't go on orbit around the Earth, but you just go up and down, and you have to go above 100 kilometers because space starts at 100 kilometers. This is according to the Fédération Aéronautique Internationale. If you go at 101 kilometers or 100 kilometers plus 10 meters, you have gone in space and you're an astronaut. If you go to 99.9 kilometers, you are not an astronaut. You have been in the high atmosphere. So you pay about, that's what Virgin Galactic Richard Branson will be asking for, $20,000 for suborbital flight in about a year or a year and a half from now. Although Virgin Galactic says since years that it's going to be next year, but this year he said again it's going to be next year. So, okay, that's one option. If you want to go to low Earth orbit or to the moon or to one of the Lagrange points or to an asteroid or to Mars or other planets or satellite, it's going to cost you $40 for low Earth orbit. And for moon and other destinations, it's going to be probably a few $billion. So some of you may have this fortune here, but probably most of you don't. So it's going to be really difficult. But of course, there's a number of billionaires in the world. And somebody who has $50 billion, and there are such fortunes existing, they may decide to spend $1 billion or maybe $2 billion to go to Mars someday. But that's going to be really, that's why I put all these dollar signs here. It's going to be really expensive. If you're a pro, and either an agency pro like NASA or European Space Agency or Japanese Space Agency, Canadian or Chinese or Russian Space Agency, then you are paid to do that. And you certainly will be, you are not paid very much, but you are paid like a good engineer. And of course it's wonderful. And you will have access to these destinations, these faraway destinations before the tourists will have. So I just want to present the two options, and I have absolutely no judgment about the good side and bad side of each option. It's your choice to be a tourist or to be a pro. Okay, just show a short video clip showing the suborbital flight. You know, you go with the rockets, you are carried maybe with a carrier aircraft, and you go up. You have to go above 100 kilometers here. And then for maybe 2 or 3 minutes, you have weightlessness here, absence of gravity, you are on free fall. Then you come down, and pretty rapidly you are back in the atmosphere. You have quite a number of Gs, like 4 or 5 Gs, come down, and you land on a runway. This is European version. This is over the Mediterranean Sea. Liftoff with some in Spain, and landing will be in, this is Montpellier, yeah, in the south of France. So this is what we talk about when we say suborbital flight. You go into space if you go above 100 kilometers, but you don't go on orbit around the Earth. $200,000. It's pretty cheap compared to what Tito and Guy Laliberté paid to go in the International Space Station, but it's lacking some of the great wonderful features of spaceflight, which is to spend hours, days, weeks in space, which is much better. This is Virgin Galactic. You see the Spaceship 2 carried by a carrier aircraft, brought to about 15 kilometers altitude, is detached, fires the rocket engine, and takes the commander and pilot and about 5 passengers in the cabin to this suborbital mission. This is a recent test just a couple of weeks ago of Spaceship 2. Virgin Galactic is preparing the second version of the Spaceship 2. The first one was destroyed in an accident a couple of years ago. But Virgin Galactic is hopeful that next year they can take tourists into space, but suborbital only. This is cool, suborbital, but I definitely recommend low Earth orbit experience or beyond low Earth orbit. The real wonderful flavor of spaceflight is when you spend hours, days, weeks, where when you can see city lights moving under you, when you see sunrises and sunsets, 16 sunrises, 16 sunsets per day. This is the real flavor of spaceflight. And these 3-4 minutes of weightlessness, this is not enough. You want to experience it for a much longer time. Okay, I want to show a brief video clip to illustrate what I'm talking about. This is taken from the International Space Station. This is the Earth at night, but you only get what you're going to see here. This is accelerated motion of the International Space Station. It's taken with one picture every 5 seconds, brought back together. You go about 10 times faster than the real speed of the ISS. But look how wonderful it is. Oops, hold on. And there's beautiful music in the background. Look at that. Northern Lights. This is structure of ISS, and this is the Earth at night. This is orbital flight. Thunderstorms here. This is the air glow, about 100 kilometers altitude, a region of luminescence in the high atmosphere. This is over the Indian Ocean. The solar ray of the station are tracking the sun, although the sun is below the horizon, but they will have the proper position at sunrise. This is wonderful. This is unbelievable. You don't get that in suborbital flight. Look at the Milky Way. These are thunderstorms here. Look at the stars rising in the east. This is magic. This is planet Earth. This is the eclipse of the sun by the moon and the shadow of the moon on the surface of the Earth. This is England, London, this is the Netherlands and Belgium and Germany and Poland, and soon will be over Russia. And again, this is accelerated about 10 times. This is a moon set. So wonderful. Look at this Northern Lights, so beautiful. Always with a lot of dynamics. It's moving around very, very fast. This is over Canada. Remember that crater here? Look at that. Over the Indian Ocean. And these vertical lines are the lines, the field lines of the magnetic fields, nearly vertical in the polar region, close to the north magnetic pole and south magnetic pole. This is going to be sunrise very soon. Thunderstorms again. And you see a comet here. The tail of the comet is always opposite the sun. So before sunrise, they saw that comet here, and then the sun is rising, pushing with the solar wind the light particles of the nucleus of the comet. Look at that. This is northern lights filling the whole field of view. It is absolutely stunning and beautiful. This is another pass over Europe, England, London, Paris. And you have Zurich somewhere here. Coming over Germany and Poland. Beautiful. Okay, just the difference between the tourists and the pros in terms of training and preparation. The style, duration, depth of your training depend on the type of mission, on the level of responsibility. There is relatively little training for space tourists. They ask for training, they ask for spacesuits because it looks more like an astronaut, but there will be relatively moderate training. You have a little training as a passenger of an airliner. You have to know how to put the life vest and so on, how to unbuckle and buckle your seatbelt. There will be more than that, but not that much more. Some zero-G and high-G training, I'll show that in a few minutes. And then for pro astronaut with significant level of responsibility, spaceflight training. And this is important that you understand that. It's much more mental and behavioral training than physical. More time in the simulators than in the gym. And a good fraction of the time spent in simulators to resolve problems. Nominal missions are normally relatively easy to perform, but you expect a lot of problems and you want to be ready to cope with this problem and still accomplish the mission objectives. Now, whether this is for tourists or professional astronauts, there's some high G and zero G training. We use centrifuge. This is Chris Hadfield, Canadian astronaut. This is a centrifuge used by the Russians still to prepare astronauts and cosmonauts mainly for the high G forces they have during launch and during the re-entry. This is an example. This is a picture of somebody who has been exposed to about 30 G for a very short time. So it's not very comfortable to have very high G values, but don't worry, you will never get that high value. Maximum 3, 4, 5 Gs maybe. The shuttle was much more comfortable. During the re-entry, we only had 1.5 G. But if you want to get the high G training, it's better rather than go in a centrifuge to go in an airplane. I mean, we're operating former military airplanes. They're becoming civilian. This is in Payerne Air Force Base. I was flying that airplane for a while as a civilian airplane in Payerne from 2004 to 2014. And now we also have a Mirage 3 flying, and you can experience these G forces in a much more pleasant way using an airplane. Come to Payerne and talk to us rather than go in a centrifuge. Now for 0G, the training for 0G is normally done in airplanes following the reproduction of free fall trajectories by a well-controlled parabolic trajectory of the airplane. So here you need to pick up speed, and then you lift the nose about 60 degrees nose up, and the crew is pushing on the control column so as to generate 0G in the airplane for about 20 to 25 seconds. By the way, there's a company in France called Novespace operating an Airbus 310 and offering this kind of profile for either scientists or for tourists. And they will be in Dubendorf. It's going to be the 12th and the 13th of June, because the University of Zurich is using this facility to do experiments in 0G without going into space. There's a little video showing what's happening here. This is the Novespace Airbus 310 flying in like a normal airplane, but it's going to lift the nose up, power forward in order to generate these 0G conditions. Again, the idea of 0G has been said already before. Zero gravity in a spacecraft is because you're on free fall. Here they reproduce the free fall on that parabolic trajectory, again for about 20 seconds. So the crew puts the throttle forward, pulls on the stick, and the Airbus 310 is going to take to make a maneuver that is unusual for an airline type airplane. Normally airliners don't do that, but this is look at that. Isn't that amazing? Okay, that's about it. Now you need to start pushing. You can't do this too long because, of course, the thrust is much less than the weight of the airplane. You need at some point to push. Look at that. This is cool. And 20 seconds is a reasonably long time. You have the time to do some maneuvers and really enjoy the absence of gravity. And the cost is about 7,000 to 8,000 Swiss francs for a flight with 15 parabolas. So it's significantly cheaper than a flight on Virgin Galactic. Of course, it's a shorter time of zero gravity, but it's affordable. Look at that. Isn't that cool? Then at some point, there's a warning that there's the end of the parabola. There's 1 G for a while, then there are 2 Gs in the bottom, but that's not too painful. And then you do it to the next parabola. Take anti-motion sickness drugs, because it's kind of provocative. I myself, when I go in the 0G airplane, I take anti-motion sickness drugs. It's much more provocative than space flight, where you go, you have 3 Gs maximum, then 0G, then you stay in 0G for a few days or a few weeks or a few months. But this is alternative of 2G and 0G is quite provocative. This is cool, really. Okay, there will be a possibility also for space tourists to do spacewalks. And of course, professional astronauts do that. In fact, here we were training in 1999 for the 3rd servicing mission of Hubble in a large pool at the Johnson Space Center, Houston. That's a very high fidelity model of Hubble. We could get also inside Hubble and operate instrument inside Hubble or exchange gyroscope or scientific instrument. And we have a spacesuit which were pretty much the same as the one we use in space, always the same differential pressure between inside the suit and outside, because that determined the rigidity of the suit. And always 2 astronauts here. There's one coming inside Hubble, the other one is approaching this workplace at the end of the robot arm on the platform with the tools here. And the tools we're using in the pool were exactly the same as the one we use in space. The idea was to reduce the surprises. If you go up in space, you work on Hubble, complex maintenance, you want to minimize the surprises. If you come out the outer hatch of the airlock and you see Schleuse for airlock, and you see exactly what you've seen in the pool 20 times or 30 times, you get confident you can do it. That's the impression I had. A few words about the basic qualification requirement for professional astronauts. I'm talking about professional astronauts. I'm going to summarize it. You don't have to read it completely, but they want to have people who have a degree in engineering or science or medicine and at least 3 years of experience after obtaining the diploma or the license from the university. ESA or NASA, they don't take people directly from university, however bright they are. You need to prove that you can work in a lab or in the industry for a while before you can apply. And you need to have a pretty good health and mental stability, in a way. This is verified during the selection. You have all kinds of tests where they verify that you don't panic when things go bad. And you are able to establish priorities. When you have a multitask thing to do, you need to establish your priorities and not panic. Now, last thing here, because many people ask the question about the eyesight. The eyesight has to be perfect, but it can be perfect with corrective lenses. If you have an eyesight that is not perfect, but with lenses it becomes perfect. In the US, they say 20/20 for perfect vision. That's okay. In the past, they wanted people who had perfect vision without glasses. Now they accept glasses, but it has to bring you to perfect vision. Now, this is a picture that was taken at the Johnson Space Center during the preparation for the first visit to Hubble in 1993. This is Commander Dick Cavey. This is Jeff Hoffman in virtual reality, the co-pilots Ken Bowersox and Katie Thornton. I'm here operating the arm in virtual reality. I'm taking Jeff Hoffman in virtual reality in the proper position to do a certain task on the telescope. And Jeff, he sees the stars, he sees the Earth, he sees the payload bay of the shuttle, he sees the telescope, and we use virtual reality. But this is virtual reality of 1993, so it was relatively crude virtual reality, but we used it a lot before going to the pool to train, as I mentioned before, which is pretty expensive and tough. We used a lot of virtual reality. You expect that in training, you train in simulators, you train in the water for spacewalks, but you spend a lot of time in virtual reality and also a roundtable to discuss how we are going to do certain operations. There's a lot of discussion within the crew and with technicians and engineers how we're going to do the mission. In fact, when a crew is assigned for a flight, we were assigned at the end of '92 for the first visit to Hubble, which took place in December '93, so 1 year training. But during this year, it was not only training, it was also design of the mission. We work with engineers and scientists and technicians in the design of the mission, especially if it's something we have never done before, which was the case in this mission. Training in simulators, this is for Soyuz. Of course, the shuttle has been discontinued in its operation since 2011. And now to take people to the International Space Station and back, we use the Soyuz. That's training in the Soyuz simulator in Russia. This is a Japanese woman astronaut training on the robotic system, operation of the robotic system of the International Space Station, where you always have a translation hand controller here and a rotation hand controller. NASA has been very strict about that. You always command rotation with the right hand and translation with the left hand, whether it's on the manned maneuvering unit of Bruce McCandless I showed before, whether it's for the robotic system. That's a rule. You get accustomed to that. It's like in an airplane. You have the stick on the right hand and you have the throttle, which is translation hand controller on the left hand. This is cool. Yeah. Robotic system. And on the International Space Station now we have the control station for the robot arm of the station inside the cupola, where you have windows where you can see outside. But before the cupola was installed, that was about 2005. But before that, the robotic system was operated from inside of the US lab using video views only. So it was pretty difficult to operate that arm without anti-collision software, based only on the basis of views from cameras. Okay, launch. Unlike what was said before, Gagarin who said that he's not afraid of the launch. Launch is scary, but don't say it if you ever experience it. Say that it was cool, there was no problem, you were completely calm. But it's really scary. And the whole ascent to orbit, which with the shuttle lasted about 8.5 minutes, it was pretty scary, especially the first stage with the 2 solid rocket boosters attached to the tank, which were the cause of the Challenger accident in 1986. This is a nice view. You have the 3 hydrogen engines and the 2 solid rocket boosters. Just say that it's a cool experience to launch, but in fact it's scary. Now, I'm sure the ones of you who choose and are accepted to be astronauts are probably pros, because that's going to happen for tourists in a very, very long time from now. You will leave the low Earth orbit someday in the future. And when you leave the low Earth orbit, that's what you see. This is Europe at night, and this is a sunrise in the Middle East. That's a magic view also. It has been somewhat retouched because they removed the clouds here, but it's beautiful. Beautiful. And maybe you'll see the Earth like this, like the Apollo astronauts saw the Earth, a little blue, white ball, like a spacecraft with 8 billion crew members and no captain. This is impressive. Yeah? And maybe you'll see the Earth like this. This is a picture taken with the Cassini spacecraft, which was operating around Saturn for about 10 years. And this is Saturn itself. These are the rings of Saturn, one ring that has been discovered by Cassini. This is the Earth over there. Of course, you'll tell me, how can you prove it, Mr. Nicollier, that is the Earth? In fact, if you look at the original, you see 2 little dots. There's the Earth and the Moon. Here you don't see it, but maybe the ones of you who are bold enough and will become pro in the near future, you'll be able to see the Earth like this. Not in the near future, in a few decades from now. One of the prize destinations beyond low Earth orbit and the Moon is Mars. Mars is observed a lot with a spacecraft on orbit around the red planets and around, with the rovers and robots on the surface. You see there was liquid water on the surface of Mars in the past. That's clear. Right now it's pretty dry. There's some ice, some water ice, and some CO2 in solid form also in the poles, but basically it's a desert. So if you go to Mars, try never to be left alone on Mars, because then you need to survive, you need to grow potatoes like a cinema movie. It was a cool movie, by the way, but try not to be left alone. And always properly attach your safety tether when you're spacewalking. When I look at this picture, I get really scared. This is like a nightmare. Because if you go spacewalking and you have not properly attached your safety tether and you are detached from the surface of the spaceship, whether it's Hubble or the International Space Station or the shuttle, and if you are in this position, you cannot do anything. You become yourself a satellite of the Earth, but only, well, you become for a very long time, but your lifetime is going to be somewhat reduced with the quantity of oxygen you have in your life support system that you have in the back here. So when I look at this, this is like a nightmare for me. Maybe you find this fun, but I can tell you this is a nightmare for an astronaut. You always need to hold the structure, and you can sometimes let it go, but never push it and let go and detach your safety tether. That'd be really a bad idea. That's an advice for the ones of you who will become pros or tourists. Never let this happen. Go to space. It's an amazing experience. So look at this spaceship. This is a nice artist view of a spaceship over a satellite of some planet, imaginary planet, and look at this. You want to be in this position here. This is wonderful. I recommend it very highly. Thank you very much. And we always remember Yuri Gagarin, who opened this door for us. That's a wonderful picture. Yeah. I have the shuttle launch picture. Is that time to show it?
Oh, no, I thought we showed it with Ben. Can we show it with Ben?
Yeah. So where are the mounts?
No, we'd like to invite everybody up onto the stage.
Okay.
All the speakers on stage, so please stay.
Yep.
Thank you so much, Claude. This has been wonderful. Okay, so because it's very, very late, we realize that some of you might actually like to catch a connection home. We're going to bring a close to the formal part of the evening, but the bonus is that we're going to continue on after we've actually done the formal ending of the event with Ben Moore and Claude Nicollier to have a discussion together, because what we thought was we have this beautiful balance here between theoretical astrophysicist and practical astrophysicist with you're both very much in the same realms, but maybe viewing it from different perspectives. Yes, exactly. So we're really looking forward to that conversation. But for now, we'd like to invite the speakers onto the stage, because we'd like to thank them very much for making such an effort to make such
Giulia,
wonderful presentations.
I cannot see Maria. And
I know Kamlesh is needed to leave already.
So don't be shy, please. You have already done. Where is Jörg? Can you come also? Thank you.
So I hope that everyone enjoyed the evening and was enlightened and discovered something for the evening. Oh, this is for you. Thank you very, very much. And if you like the evening, please let Valentina and I know, because this is the first time that we've organized such a large event for Yuri's Night. So we're very curious to see what people thought of it. And yeah, Claude's already suggested that this should happen every year, probably in different cities. And we would be most honored if he would join us for future.
Yeah, no, the idea is to do it every year somewhere in Switzerland. We did it the last couple of years at EPFL in Lausanne. The flame was taken here in Zurich to do it this year, and it was very nice. It was wonderful. It's somewhat different from what we did in Lausanne, but I think it's great to see the variety, and we could have Basel and Bern or other places organize it next year. But let's try in Switzerland to have the 12th of April every year in events, Yuri's Night. Do you agree with that?
Great.
Good. Okay. So I think we are going to move to the discussion. If someone wants to leave, please feel free. I can totally understand. Okay, so the stage is for you, and Ben.
Thank you.
Yep.
Okay, can you well, yeah, but
do you want a minute?
Can you start this presentation?
Oh, yes,
so what is going to happen, ladies and gentlemen, if you want to stay around, I'm just going to talk for a few minutes about a topic about the future of space, in particular getting to Mars, and then I want to discuss with Claude what he thinks about the possibility, the dangers, the difficulty. Are we actually going to get to Mars? And then we'd like to open it up. If you have questions for Claude or myself, then we'll just open it up to the audience and you can fire away. You can ask what it's like to be in space. So
we're just getting a video up. Claude wanted to show us a launch.
It's a short video of a shuttle launch. I think we need tonight once at least to experience a real launch with the noise and the firing of the space shuttle main engine, the solid rocket. It's short, but it may be a good precursor to the discussion we have. Do you agree with that? Let's go. Let's try to make it work here. Okay.
T-minus 90 seconds and counting. All systems are go. We're about 90 seconds from the launch of Space Shuttle Discovery. T-minus 60 seconds and counting. We are transferring to orbiter internal power at this time. Discovery is now running off its 3 onboard fuel cells. Coming up on a go for auto sequence start. And we have a go for auto sequence start. Discovery's onboard computers have primary control of all the vehicle's critical functions. T-minus 17 seconds and counting. 15, 12, 11, 10, 9, 8, 7, 6, start, 2, 1, booster ignition, and liftoff of the Space Shuttle Discovery, returning to the space station, paving the way for future missions beyond.
Commanding the main engine nozzles to swivel, aiming the shuttle for its precise target in space for main engine cutoff.
Should have a good forward leg now and after. Okay, you sound good. Discovery Houston, negative return. Copy, a negative return.
Oops. Really an amazing machine. And after separation of the boosters, we continue to go up only for 6.5 extra minutes, and then we're in space already. And then at the end of the ascent, we have 3 Gs, and then we go from 3 Gs to 0 G at main engine cutoff within about 1.5 seconds, and everything suddenly starts to float. You know, the pencil, the notebook, everything is floating, and this beginning of a typically for the shuttle was about 10-day mission. Again, much better than suborbital flight. But if you want to go suborbital, it's your choice. We can start. Okay?
Can you start?
I have a question to ask.
Yeah.
I mean, just watching that made my heart beat.
Mine also.
Yeah, that's what I wanted to ask. When you're sitting there, is it the same for you that your heart is racing like crazy, or are you actually very occupied that you've got a job
we
to
are
do?
very occupied. In fact, I saw a lot of shuttle launches from outside. I experienced 4 being inside. And inside, it's not as emotional as it is from outside. From outside, it's much more emotional. Inside, you always try to be ready in case things go bad.
Okay.
So it's a small technical task, a mental task. We train a lot for engine failures right after liftoff, or a problem where you have the 3 main engine firing, and then there's a problem in the fuel flow of the liquid oxygen, then automatically they're shut down, but you never know what's happened in the bottom. You may have a fire because you have these enormous quantities of liquid oxygen, liquid hydrogen. You have kind of a bomb there very close to you. So we train to evacuate very rapidly the shuttle in case we have a problem before booster ignition. because if there's a problem with the main engine, the booster's ignition is inhibited, so we need to evacuate as soon as possible. So during the final countdown, I was always thinking, Claude, now in case things go bad, what do you do? In which order do we evacuate? If I have to take care of the firing of the pyrotechnics to open the hatch, then I need to know exactly where it is and what I have to do. You think about these things after the beginning of the ascent, when the boosters ignite, we are going, we cannot come back. But in case you have an engine failure early, you need to come back and land at Kennedy Space Center. If you have an engine failure later, you go to Africa and you land there in Kinshasa after 20 minutes, or you go to Spain, depending on the orbit inclination.
Like a mystery
so we think always of all these things that could happen, and we are ready to do the right thing to save ourselves, not to accomplish the mission, but to save ourselves. So it's very different inside and outside. I was always very emotional, nearly crying when I saw my friends going from outside. Inside is a tactical task, operational task.
So I imagine for the space tourists, they're probably the ones that are going to have the hearts pounding out of the chest because they don't have a task to do.
Of course, it's going to be a little different. If they go on suborbital, they are going to be taking off with an airplane. They are going to be their little spaceship, and then at 15 kilometers altitude, the spaceship will be dropped, and then they fire the rocket engine, but it's going to be much smoother than a liftoff of the vertical, like the shuttle or Saturn V. But still, I mean, heartbeat, but now they don't measure anymore on the shuttle, or on Soyuz the heartbeat. They figure out it's not really needed because people brag about low heartbeats or try to hide their high heartbeats. So they thought it doesn't matter. As long as people are healthy, if your heartbeat goes to 120, that's okay. If it stays at 75, that's okay too. If it goes to 150, that may be a little high, but that's okay, you will survive. You know? They don't measure it anymore.
So, Ben, if anyone would like to ask questions, really burning questions, I can come around and ask, but otherwise, you... sorry?
The little presentation.
Oh, yes, of course, sorry, that's right. Sorry. Ben has a small presentation to introduce what is going to be discussed. Just one moment, I need to switch computers.
Do you need the other computer?
Yes, I do.
So I'm writing a regular column for the Tagimarki, and I thought I'd take this great opportunity to get some of that knowledge from Claude and his feelings for space. And in particular, I want to write about what is this passion about going to Mars, and can we actually do it? And I'm going to give a sort of a little bit of a negative perspective on this, but then maybe Claude is going to give a more positive perspective, and then I'm going to put this together and write it up and send it off, and maybe they'll publish it, but we will see. And the story begins. So I've been a scientist in residence here for since Cosmos opened, and if you remember, I don't know, some of you might have been to some of the Science Late shows that I did, and these will start again in September. It's a late night science show, a humorous look about what recent developments in science. I'm not going to do that now, but I'll just take a little segment of what I talked about, because every late night science show we have a little feature on Elon, and this is fun because there's always something happening. Elon likes to be in the news. Elon Musk is just a great guy. We all love him, but he's funny as hell. So, and as Claude said, you know, this is a dream of many people to go and walk on this barren, dusty rock. And I just, for me, find it really horrifying. There's no bars, no pubs, no restaurants. It's really a dull, boring place to go to. But our friend Elon says it's like SpaceX is going to get you there by 2030 with hotels and bars and a colony of people. And he says it'll be like really fun to go. You'll have a great time. And I'm just going, I don't know, Elon. Let's just go through a few checklist items first. So I made these little checklists. Can we actually get there? Now, the first thing, you need some good books for the journey, because it's going to take you about a year just to get to Mars, a year in a very small space with some people that you might not actually get on with very well. So you need some good reading material. So one thing I found was this lovely board game, Terraforming Mars, which you can play with your astronaut colleagues to keep you busy. And it's quite nice because it goes through all the instructions. When you get there, it's going to take about 10,000 years or more to actually terraform the planet to become habitable like Earth, but you'll have a good background knowledge to get there. Now, spacesuits. You know, the suits that Claude was wearing in space, they cost over $1 million each. They're very expensive. We don't even have one for Mars environment yet. It's going to be bombarded by radiation because of the thin atmosphere of the world. But I did find something that we can use already. We don't need to actually develop anything new. We can just look at some science fiction. Robbie the robot, that is your spacesuit. It's going to look so cool walking around Mars on that. It's going to protect you from the high energy cosmic rays. No problem. So a tick mark on that for Elon's checklist. Now, jet lag pills. Now, this is a problem because Mars day is 40 minutes longer than Earth, which means that every week you're sort of half a day out of sync. And this goes on for eternity. So if you spend more than a week or two on Mars, you're going to be permanently jet lagged. You're going to feel like crap. And there's no known medical cure for that. You're just going to have a really bad time. You're always going to be tired. A Mars tent, well, habitat when you get there, well, that's, you know, we can solve that problem. You just need to send some, you know, building construction materials in advance. A vehicle for Mars, well, we've already got that. When I gave this presentation last year, Elon had just tweeted this about sending his Tesla to Mars, and no one really believed he would do it, but he is the guy. He did it. And I unfortunately made the comment in my talk about, well, I wouldn't have sent just the car into space, I would have sent Donald Trump, and of course there were some Blick reporters in the audience, and they put this on the front page of the Blick, and they don't really get humor here in Switzerland, but that's British humor. Anyway, I thought it would be much better to send Donald Trump into space than a Tesla car. But there is a vehicle there ready. Unfortunately, it's not going to reach Mars. It's probably going to crash land on Earth in a few years, but not too bad. A communication system. It's 20 minutes for light to get to Mars. So forget having a phone call with your loved one back home, and you're not going to be able to play video games at all. 20 minutes to get a communication back and forwards. It's going to be pretty lonely out there. Food is no problem at all because at the ETH Zurich they're developing this wonderful machine here. It's a cyanobacteria tank which spits out little blue pills of protein, and that's going to feed you for the whole year's journey while you're there and on the way back again. Very nourishing, good for you, and it's animal friendly. Medical equipment. Can you imagine? You halfway to Mars, you're looking out at the universe and it's all cool and wonderful, and you get a toothache. And you know, you can't call ESA or NASA, you know, take me home now because my tooth's hurting. That's the worst pain ever, you know, one amongst them all. You're gonna have to fix it yourself, but that's no problem. You can take one of these medical kits with you and you can just pull out your own teeth and sort that out. But, you know, these are problems that you have to deal with on this length of a journey. I mean, this is a serious trip, a year to get there. And, you know, let's not talk about getting back. A rocket for the journey, well, Elon has proposed that. It looks something like you would use at nighttime in bed, but this is the BFR, the big fucking rocket. And it's under development. It's great. It's even bigger, you know, than the rockets we used to get to the moon. So that is there. We've got that. Still need to develop a life support system on the rocket and something to land from the rocket onto Mars and to, if you actually want to come back again, to bring you home. So this is all a big difficulty, but the biggest problem is money. You need a lot of money. The Apollo moon landings costed, in today's money, $150 billion to the moon and back. Wonderful accomplishment, but it's expensive. Getting to Mars, even Elon, with his genius, he's halved the cost of space launches using reusable. With those improvements, it's still going to cost about $500 billion to get to Mars and back. Who has that sort of money? The top 10 people in the world you've got $500 billion. Now, if you notice, Elon isn't actually on that list. Elon, a poor guy, is only worth $20 billion, but he's getting there because he had the genius idea of selling flamethrowers with the Boring Company, and he sold 20,000 of them for $500 each, so he's got 20 million extra, so he's on the way there. So that's my pessimistic view of getting to Mars. Thank you very much, ladies and gentlemen. I'd like to invite Claude back onto the stage. So, I think we will get to Mars. By 2030, I'm not so sure. What do you think, Claude? Are we going to get to Mars by 2030?
Yeah, probably a little later than that, but sometime before the middle of the century, I think we will. But Elon Musk is Elon Musk. You know, obviously he is kind of alone thinking the way he is thinking. I think exploration of Mars will take place, but it will start the right way. It means that we will first explore, send only a few people so that they can verify what is the lifestyle on the surface of Mars. If we can grow agriculture in the greenhouses, if the quality of life, if they spend months, maybe a year or a year and a half on the surface, is such that someday we can think of sending colonies or a large amount of people. I think that the beyond the low Earth orbit is to verify long term. When I say long term, it's not decades, but centuries. If someday human beings can become a species that spreads in the solar system, in 500 years, in 1,000 years, in 1,000,000 years maybe, our descendants, that's what we want to verify. Is it a step in the evolution, the Darwinian evolution, so that eventually going into space will give us a better chance for survival? We don't know now, but if we don't go at all, if we stay only on low Earth orbit or say, well, enough problem on the Earth, we stay on the Earth, we don't go back to space, then we miss the opportunity to verify that. That's the way I would put it.
Yeah, I absolutely agree with that. We have to become spacefaring, or as Carl Sagan said, we will become extinct. We have to leave this planet at some point.
If it gives us a higher chance of survival in the long-term future, I talk about the long-term future, it's worth doing. And in a way, we can't resist it, we have to do it, because Darwinian is something that happens not on the basis of decisions that we take, but it just happens.
Yeah, absolutely. So all these technical
That's a different perspective, you understand my point?
Yes, yeah, absolutely. It's something we should do, aim towards, and at the moment we have a lot of problems to overcome, all these technological problems to do that, but it's also going to be a learning process.
In a way, we have the time. I don't think we should rush it.
Yeah.
I don't think we should rush it.
But there is a rush, because after Elon tweeted this, Boeing said, we're going to beat you, Elon.
But this is Elon, and Elon is a businessman. You know, I know he has a lot of money, and he spent his own money, although we have to remember that SpaceX was created on the basis of a lot of money given by NASA to Elon Musk and to SpaceX, so that they provide transportation from the station, which they're about to do. They've done it for freight since a few years successfully, and they plan to do it for people starting next year. Elon Musk and SpaceX were helped by NASA because NASA needed them. So it's not really a competition, it's a cooperation, although Elon went way beyond what NASA asked for, typically this idea of a colonization of Mars, which I don't agree with. We need to go explore and try to figure out whether colonization is someday going to be possible. And the terraforming, of course, is an idea. Maybe in 200 years or 500, we'll be able to do that, not the next decades.
But at the moment, it's people like Elon that are actually going to do it, because, as you well know, the budget of NASA and ESA added up together is totaling 40 billion a year, and all of that is spent on Earth monitoring systems. So the amount of money that's left over for grand missions like Mars is just a few billion. It's way off the hundreds of billions.
We are not in a huge hurry. And either you do things progressively, typically NASA and ESA and the Russians and Canadians and Japanese, the ones who cooperate in the International Space Station, put their funds together in order to, within the next 20 or 30 years, have joint international exploration mission to Mars. Again, I say exploration. With maybe 5 people, 6, they will take a risk. That's going to be a dangerous mission. That's going to be exploration. This is what we have to plan for the relatively near-term future, not the colonization. Colonization may be, but that's way beyond. Yeah. That's my opinion.
Yeah. Would you go to Mars?
Yeah, I think I would go. I would, yes. I think space flight, you become so attracted to it that I would go. I would definitely go. Super. I would have to ask my daughters. But finally, the time you die, if your body is on Mars, on the surface of the Earth, it doesn't really matter. At the scale of the galaxy, it doesn't matter, or even the solar system. Yeah? Go there. Of course, I have an age such that if I go, probably I would not come back. but that's okay, I think.
Yeah,
that's my personal opinion.
A beautiful point to pause and hand this over to questions from the audience. I just have one question from an audience member, which I thought particularly nice, and then I will turn it over to you. Do you dream of space at night when you dream? Do you dream of being in space?
Yes, I do. I do sometimes. I dream of flying, and I dream of space. For the flying, I dream quite often that I can fly with my own hands and arms, come from a hill, and because this is a dream from a long time. In a way, Yves Rossi, has been able to achieve that, although with motors under his wings. But the idea that human beings can fly by themselves has been always very present in my mind. And I dream sometimes of space, of being on orbit, but by myself, pretty much like Bruce McCandless, but even without a spacesuit, because this is allowed in a dream.
Beautiful. Thank you very much, Claude Nicollier. Inspirational. Thank you very much.
Thank you.
So, ladies and gentlemen, if you have any questions for anybody here, myself, Claude, please fire ahead.
Hello? Yeah, that's okay. So just a question. You say that maybe there is no rush because we have time. We may find the way to get to Mars or to expand in the universe or whatever. But do you think that we have the resources or the technology at all to go there? Because in principle, we are reaching some plateaus in technology, in things, at least some people can say that. And so can it be like a bottleneck to some extent?
Yeah, resources is very relative, because we see that with the private companies, Elon Musk and Jeff Bezos to a certain degree also, it looks like the price of every kilogram brought to low Earth orbit is coming down. That's a fact. And the reliability of the launches with Falcon 9, Falcon Heavy, we don't know, there was only one flight, seems to be reasonably high. Of course, he's using relatively crude technology. These are kerosene burning main engine, as opposed to the shuttle, which was using the cryogenic engine, which are much more expensive, but they produce water and thrust. That's an advantage. So the prices tend to go down. And I think for tourist flight in space, like in aviation, when we started to go across the Atlantic with the DC-6 or DC-7 in the early 50s, it was costing $20,000 or more. Now it costs less than $1,000 to go to New York and back. So the prices will go down with time. It will still require a lot of resources, but resources are always very relative. If you look at the money, the tens of billions that were spent to save Greece from a bad financial situation. If you look at the expenses for the Department of Defense of the US, which is more than $650 billion per year, if we are smarter about using our resources, we could direct them, especially the cost of defense, although right now we don't have a situation that is becoming calmer from a point of view of the tension between big nations. But someday we may become wiser and we will have the resources to do it. So again, this is all relative. For me, a staggering number is the number of billions of dollars used for defense in the United States. It's been increased significantly by the president now, by Donald Trump. This is sad, very sad. So the resources there are, it's just a matter of properly using them. And I still am hopeful that in a few decades we'll be wiser than we are now.
Good answer.
I hope so. Any other questions? The lady there.
What makes you say that we have time, actually? That we have time, there is no rush. What makes you believe that?
What makes you think that we have no rush, that we have plenty of time to explore?
Well, it's, I'm talking especially about the flights to Mars, and this idea of verifying whether we can colonize Mars or not. The exploration is a response to the curiosity we have. Curiosity we have about the universe, and we built all these fancy telescope on the ground and in space in order to answer all the questions we have about the universe and about the big question, are we alone in the universe? We spend quite a lot of effort and money on this. And going to Mars as a step towards the verification that long-term, we as human beings can become a species that spread in the solar system. I don't think we're in a big hurry to verify that. We need to do it progressively with some goals on every step of the journey, but we are not in a huge hurry to do that. However, the exploration of Mars, to better understand Mars, better understand what happened on Mars, why we had water, why we don't have any more, why we had an atmosphere, it was blown out by the solar wind, it seems that's at least one of the theories. Answer to this question about the solar system, we try to get these answers pretty soon, but most of these we can get with robots and with rover, or with spacecraft on orbit around these planets. But the idea of verifying whether we can colonize Mars, we are not in a hurry to answer that. That's my opinion. But exploration with small group of people who take a lot of risk, and maybe they will die. If it's a small group of explorers, it's permissible. They accept that. If it's a large colony of people, we cannot accept that they have a disastrous quality of life and that they will die early because not enough capability for tracking their medical condition and taking care of their health, or food supply insufficient to ensure a good health on the surface of Mars. That's a colonization step, and this, to my point of view, we're not in a hurry to do that. But exploration, yes, we should pursue that.
I really want to know what it's like to look at the stars when you're in space.
What it's like to?
Just look at the sky at the stars. You showed a video.
For
with
me, this was a very, very impressive sight, the sky. In fact, most astronauts talk a lot about the views of the Earth, which are beautiful, of course, and they've seen a lot of pictures. There are a lot of very good books about this. But the views of the skies are very beautiful, and you saw some on the movie that I've been showing, although it was accelerated. But you see the sunset during the orbital day when the sun is above the horizon. You don't see any stars or planets in the sky because the eyes are in the day mode, and they don't have the sensitivity to see the celestial objects, faint stars and planets in the sky. And then the sun sets, and within minutes you see rapidly moving, not as rapidly as you saw in the movie, but still pretty rapid motion of the sky. And in a way, the sun sets. If you are prepared with getting dark adapted rapidly, like wearing dark glasses during the end of the orbital day, the sunset, you remove the dark glasses, wow, you see the stars. And in half an hour, you see the whole sky, the constellation of spring, summer, fall, and winter in about half an hour. And it's really amazing for somebody who is touched by the beauty of the sky to see the whole sky in half an hour is really amazing. Providing that we have the proper orientation of the shuttle, of course, we need to have the large windows, which were the overhead windows, up. If we are payload bay down, the large windows are down, we see only the Earth, which is fine. But if you want to look at the sky, you need to have the proper orientation. But I was very impressed with the beauty of the sky seen from space. And there's another element. You saw this air glow, the light emission of the high atmosphere, about 100 kilometers. And when you look at the sky, even from a mountainside, when the sky is perfectly clear, no clouds and no haze, you always have background light over the whole sky because of that emission of the high atmosphere. When you're out in space above that layer, which is only at 100 kilometers, so you're always above it in low Earth orbit, the background of the sky is completely black, which means that everything that is diffuse and low light level, like the Milky Way, stands out much more. And I was really amazed, impressed profoundly by the beauty of the Milky Way seen from space. I had the feeling of seeing the third dimension of the Milky Way, the depth of that disk of stars and interstellar matter within the galaxy. It was really amazing. I was emotionally struck by that. So, great beauty of the sky seen with the naked eye from space. If you take the proper precaution, typically getting dark adapted during the end of the orbital day so that the sun sets, you remove the dark glasses, and you have a sky which is absolutely superb.
Claude, we've just put a photo up that shows the blackness behind you.
Yeah, and this is interesting picture. This was taken during my last mission in '99. We did spacewalking with Mike Foale for 8 hours to replace the main computer of Hubble and one of the fine guidance sensors. And you see on the upper part of the visor of my helmet, you see the reflection of the Earth. So I had my head down, which is not a problem because you always have the feeling that down is where your feet are. So for me, down was where the payload bay was. But if I was looking up, I could see the Earth upside down, which was not disturbing because I still had the feeling down is where my feet are. This is a celestial body above me, beautiful, with the dominant colors blue and white. That was a special moment. I'm using a power tool to remove the main computer from a thermostabilized container in the payload bay of the shuttle. So my feet are down in the payload bay. And all of these we had trained in the mock-up in the water. And I knew exactly how to put my feet in this position. So without using a foot restraint, I could use both my arms and hands in order to do the work. The problem is if you cannot stow your feet somewhere, you need to hold a handrail or a piece of the structure, and you only have one hand remaining to do the work, so which is difficult. You always try to stow your feet somewhere so that you can use both hands and both arms. That's a wonderful memory. Now, just one remark. Some people have said, Claude, why do you have the American flag on your shoulder, not the Swiss flag? In fact, we asked for the Swiss flag, but too late. This is about 2 months before the mission. NASA said, oh, it's far too late. We have all the documentation such that we cannot change it. I said, that's fine. That was not a big problem for me. In a way, it has been more a problem for some of my compatriots, for the Swiss, who said, Claude, you should have had a Swiss flag, which is true, but it didn't matter too much for me. We were all working together. Yeah? But just an explanation about why. It's not my choice, really, but it was thought about it too late. And ESA, I was in Houston, Johnson Space Center, Houston, ESA in Paris, and in the Germany, the European Astronaut Center. They did not care too much about me. So they should have taken care of that, in fact, because I was really working hard, preparing for the mission. I thought about that too late, but ESA should have thought about it. I'm a little disappointed they didn't do that. That's a small problem.
I'm really interested in the how you behave among the team in space, how you deal with discussion, or what was your biggest discussion among your team in space?
You mean within the crew?
Yeah.
It was always very friendly. Of course, we trained for a year. We spend a lot of time in the simulator where the whole crew is there. And we are always in the simulator facing problems. There was never 5 minutes without the problem being ejected by the instructors in the control room. So we always have to handle problems, sometimes big problems where we can lose our life if we don't do the right thing. So we learn to work together in a normal situation, in adverse situations, so that we maximize the likelihood of accomplishing the mission objective, and if it's not possible anymore, to survive. That's a rule. And if you start fighting, arguing, elevating your voice, then you reduce somewhat the likelihood that you'll be successful in solving these problems. So it's always very smooth. And you know, one very good example is Apollo 13 on the way to the moon. Bang! The oxygen tank explodes in the service module. And the commander, 30 seconds later, Houston, we have a problem. And with a very calm voice. And this is typical. When you have adverse situation, you stay calm. And also within the crew, you just look at the situation, you see what can be done. Sometimes there's an immediate action that is necessary. Typically, if an astronaut moves away because he did attach his safety tether and he detached from the structure, then of course we don't think, what are we going to do? We just go and rescue him, that's clear. But in most cases, we stay calm and we look at the situation, we see what has to be done, and we work together within the crew. The crew represent different skills that are represented by each of the crew members with some overlap in the responsibilities. So if somebody is incapacitated, we can still do the mission. But if the commander is never, and I always had good commanders, is never imposing his own view. If it's a problem with spacewalking, his 2 or 4 spacewalkers have much more experience. He relies on them, and there is trust and respect.
Claude, does that make it impossible for you to bear watching sci-fi movies?
Yeah, in fact, Hollywood has not really understood that. Because if you look at Gravity, the spacewalking in Gravity, or even at the end of The Martian, which is a good movie, but at the end it happens on orbit around Mars, and here also they are moving so fast and they are yelling, and so this calm attitude, even in dangerous situation and adversity, Hollywood has not understood that, except in Apollo 13, but that's not science fiction. This
was based on a film. On a true life. Actually, I have a funny story about that. When I did the zero-G flight, it so happened that Ron Howard was there, and he was sending his wife onto this zero-G flight because he said, well, I did it like 20 years ago, so it's her turn. And so I said, well, Ron, I have to tell you something, actually. My daughter was quite young, 11 years old, and I was trying to convince her that it would be interesting to watch Apollo 13. And she said, oh, I don't know about that. And so finally one night we watched it, and when I put it to bed afterwards, I said, so what did you think of the film? And she said, oh, it was really interesting. I said, well, I'm glad. But you understood it's actually based on a real life film, a real life story. It actually happened. She said, what, really? So it was just the 4 astronauts up there. I said, hang on, 4, no, there was 3. And she said, yeah, the 3 astronauts and the cameraman. So Ron Howard was quite pleased to hear this.
No, but I think Apollo 13 movie represent well the reality and the strength of Gene Kranz, the flight director. He gathers his people. He says, we're going to save the crew, and failure is not an option. Very strong words and really wonderful attitude. It's this is the way things happen. Total respect, trust, and strong decision going the right direction to either accomplish the mission objective. We try to do that. If we cannot, save the crew.
I think my understanding was that they actually had to consolidate several different real-life people into singular characters because there was actually teams, but for a film's sake, it's easier to concentrate on just one character.
Yeah.
So,
I mean, in the whole human spaceflight's adventure, the human relationship has been for me a wonderful experience. And in a way, in my relationship to people now, I think I've changed positively after having gone through all of this. Typically, I put forward very strongly the respect and the trust. And it's not always the case in all human activities here on the surface of the Earth.
So would you say that your personality has changed since you...
Yeah, I think so. In being much more open. And also this idea of the respect until people don't deserve any more respect, but it has to go pretty far. I don't have a huge respect for Hitler, for instance. I've not known him personally, but but the default should be always to respect people and have trust until there is an indication that trust is not the right thing. But then you try to approach the person and see whether you can regain trust. And I've been becoming much more agreeable to trying to fix things in relationships rather than turn my back and then move away. And that has been very positive experience, really, very positive. The human relationship in human spaceflight has been a wonderful experience.
Thank you so much.
Yeah.
Thank you very much, Claude. Thank you very much, Mickey and Valentina, for organizing the event tonight.
Thank you, Ben, for your challenge about Mars. I think it was very useful. I think it's good to have this kind of challenge. That was good.
Thank you.
I tried to answer.